Well, CPU registers are variables that are built directly into the hardware. We have 32 general-purpose registers in Mips architecture. Each one of them has a name, or it can also be referred to the number that follows the $sign. So in Mips syntax, $sign is used to refer to the names of the registers, and each register is an integer 32-bit size. We also have floating point registers that are visible here in this coprocessor panel right here, and they're all named $F followed by the designated number, and there is also 32 floating point registers. This panel here shows the values of registers at runtime when we're debugging the code, and you can switch between the hexadecimal values shown here and decimal values by turning on and off this check mark for hexadecimal values. Conventional usage of Mips registers is described in this column, and the first one is a constant 0, doesn't change during runtime, just remains 0. So anytime you need to set something to 0, you can use this register. The second one is a temporary value, but it's reserved for a number of pseudocode instructions available in Mips. There are two registers, V0 and V1, designated as function return values. So all this usage is just conventional. You can use these registers any way you want, but most programmers follow this convention because it simplifies interaction between multiple modules and generally makes program organization easier. So every register is a 32-bit size integer, and you may be wondering why we have two of these for function return values, and clearly this is in case if you need to return a 64-bit integer, you would have to then combine these two together to form a 64-bit value. These registers here, A0, 1, 2, and 3, reserved for function arguments. We also have temporary values and another set named S0, S7 for the so-called safe temporaries. So what is the difference here? So imagine that these registers are placed inside the CPU, and they're like super fast variables that the CPU uses during arithmetic computations and other operations. At the same time, we can have a procedure that relies on all of these values to do certain computation. So then this procedure, I'll name it a caller. Okay, and so this caller wants to call another procedure named callee, as we say here, caller and callee. So caller calls the callee, and this called procedure also needs to use these registers to do its work. So every register marked as a yes in this column right here has the meaning that this callee is responsible for saving all of these registers somewhere in memory. And this memory can be a stack memory, global memory, any kind of memory outside of the actual scope of the registers. So the idea is that this callee program should not alter the values in these registers before it returns back to the caller. Therefore, at the end of the work, it needs to restore the values and put them back in every register. Okay, so every register has to be brought back to its original state, and then the callee can return back to the caller. None of this is enforced. This is just a convention. And another part of this agreement between the caller and the callee is that all registers that are marked no, the caller is responsible for saving before making a call to another procedure. So all of these registers marked as no, the caller has to be able to preserve before calling another procedure, in case if it's using these values and cares about them to be preserved upon return from the callee. Alright, so these registers also have to be saved somewhere, and then eventually they can be restored back. Of course, if the caller is not using these registers, then there is nothing to preserve and you don't have to worry about it. Okay, so that's the difference between the temporaries and saved temporaries, with the no and yes indicating who is responsible for preserving them. There are more temporary variables. There are also some registers reserved for the operating system environment. Global pointer can be designated to point to global memory. Stack pointer indicates location of the stack, which is a memory location for temporary values, and by the way, preservation of registers is very typically done in the stack memory. Frame pointer works together with the stack pointer to organize a stack frame of local variables on the stack. And return address is the register which is updated by the jump instruction that transfers control to a specific place in the program, and therefore this register contains the address where the program where a subprogram can return from the procedure call. So the bottom line is that when you're making a computation such as x plus y, it's very likely that you will have to place addresses of these variables in some of the registers, and then also retrieve their values and store them in different registers. Then choose the correct command to do the computation here, and then store the result somewhere in computer memory. So the registers are used all the time when running the computations, and occasionally we retrieve or update memory at the locations of our variables.